Okay, hi everybody. This week we're happy to have Luca give us a talk about theoretical motives, revisited and developed. So please take it away, Luca.
Okay, so thank you for the invitation, and I hope everything is going well with this talk. It's quite difficult to give talks on the internet. In any case, so this is an update of work in progress, which is now a few years, started a few years ago, about theoretical motives. And by the way, when I mean in the abstract, I mentioned mixed motives. These are not intended to be the mixed motives which provide the standard conjecture or related to the standard. So everything that I am saying is intended to be independent from standard conjectures. So briefly, theoretical motives are something that we hope to construct through a theory. So like theoretical physics, theoretical motives are theoretical, and we want to construct out of a theory. That means homology theory. And this work, of course, is coming out of other collaborations. Of course, Mike Prest and Annette Huber gave some, we wrote a couple of papers with them. And I also want to acknowledge conversation with Joseph Ayoub about this subject. So what is the main tool? So the main tool is universal cohomology. And I try to explain what is the universal cohomology, but first of all, this in some sense is split in three different subjects. From the first is some algebraic theory. And the second is what we can call ordinary theory. And the third is something which involves duality. So I would call it duality theory. So the first part is something that I already developed, and I'm quite close to provide a version, which is some sense quite nice. The second part, which is ordinary theory, is related to topological cohomology theories, and this is almost done. And the third part is still a work in progress, but I hope it will be done in the next. I'll try to explain the first and second part briefly and mention what is expected in the third part. So what is the object of everything is what I call hom underline of C into A, which is the category of homologies on C. C is any category, small category, and with values in A, which is, let's say, for us, is always an abelian category, could be R-linear abelian, Grothendieck category, tensor category, but or maybe less equivalent exact categories, or even not additive, some exact categories. So for the talk, I would like to take values in abelian at least. And this is a category, so it's in some sense functors from C to A, and collection of functors. So an object is just what you can imagine. The minimal requirement is a collection of functors from C to A. And so this is a family of functors. And of course, you might like to add axioms. So plus some DAG. This is a DAG, which is equal to axioms. Okay, so for example, you would like to have the point axiom, which says that you have a collection of points, which are like in theoretical physics. I understand that there are point objects. So point objects objects, which could be zero-dimensional or final object or weakly final object. So, but or objects, point object, and then you like to have that H star is 0 for I different from 0. This is a very basic. So if I add a decoration, I will put some DAG as a subscript. Okay. Okay. So of course, what I want to do now is to move A and to make this. Of course, these are objects, and you understand that you can make, as usual, natural transformation of these collections as maps, and you can move A in some domain category, like we take abelian. So for abelian, you would like to have exact functors between abelian category, and you can make up a two-functor of the cohomologies. Of course, this is not okay. This is not enough. So what we have in general is a slightly more refined situation where we take a relative homologies. So this is a similar category of relative homologies, and I put a square. So what is this square? This square means so relative homology over C square, where of course this is a category of pairs. So X, Y belongs to, if Y to X is a kind of, is a distinguished map in the category. Whatever is just you fix a distinguished subcategory and you make the category of squares, okay? So the maps between them are squares. And then what we want now is a collection of functors on this into A, Hi of xy, and of course we can make the additional standard axiom of the exact sequence of the triple. So we have xy, xz, and YZ. So what is a triple? A triple is just Z to Y in X, Z here. You have an F, you have an G. This is the identity, and Y to X. This is the identity, and here you have F and G. Okay, so this is you see the maps from YZ to XZ and to XY, and so we have to add to these functors another data, which is the connecting map from HIXY to HI minus 1 YZ. Okay, so this is an additional data such that we have the HY usual sequence HIX Z HIX Y, and then the connecting map is exact. And then, of course, we want to have another condition, which is the Q plus delta naturality. So it means that we have, if you have a map of triples, you can define a category of cubes instead of squares, and you can put the delta naturality is just the usual condition that the deltas are natural with respect to the maps of triples, okay? Okay, so of course, this is in some sense the free category, and then you want to put the decorations, so DAG axioms. So this is the basic thing, and then you want to put axioms, and then you get some. This is very rough, I know, but you will see what I mean in a second. So, of course, if there are questions, ask. The usual basic axioms that we want to put are the excision, and still we just have fixed the distinguished subcategories. So what I mean excision? Excision means that we collect a certain number of squares, X to Y, is some sense a CD structure in the sense of Vygotsky. So these are maps from YZ to WX, and we collect this. So epsilon is in some collection, which is stable by isomorphism, of course. And for each W, we take, let's say, something like this. And we say that these are a collection of excessive squares. I mean, I think it's quite intuitive what I mean, which is stable by isomorphism. And the excision axiom is that the induced map HI in HIYZ to HI WX is an isomorphism. Okay. The other axiom is the well-known homotopy axiom. And for this, we need to choose a cylinder functor on the category. So this is a cylinder functor, which means simply that we have I to this, some natural transformation, is a very weak cylinder function. I don't want to have anything else. For example, it could be given by the product. For example, of course, you can take IXY to be X times I, Y times I for I interval object. Again, interval object is a very weak interval object in this sense, and then you can define when two maps are homotopy under the cylinder in the canonical way. And if this is a homotopy of parallel maps, and the axiom is that they induce the same map. So this is equal to the delta I. Okay. Okay, so this is the point. One thing, I mean, that we have to note is that note that excision implies Meyer-Vettoris or CD exactness in the sense of Vygotsky. And if you have a homology which is invariant under the cylinder functor, then you say that is invariance implies I homotopy invariance. So I said before what are homotopy invariant maps, and so yeah, I homotopy invariant. And also the converse is true if the cylinder functor is given by interval in the sense of Vygotsky. So also the converse is true for good interval, Okay. So this gives what I want to call following Eilenberg. The idea of Eilenberg is to define, in some sense, a structure on the category of topological spaces, which is a homological structure. So this gives a homological structure on C, which is as I said, a distinguished subcategory, which gives the pairs, plus a class of excessive square and a cylinder functor. So this is a homological structure C, and every category has a homological structure. So it's not at all, because I can make for example, if I have a category with a final object, I can take I to be the final object. The interval can be the final object. Then the homotopy is equality of maps. And for this, so that we, for example, I can take C square equal to C2. This to be the iso, and I to be a final object. So at least I need a final object, and then this is a canonical or initial, in some sense, homological structure on C. Okay, so if I also have a zero object, So if I have a zero object, of course, we can also map C to C square as usual. As you know, in topology, we map X to X0. And if we have coproducts, we can, of course, ask for additivity. And okay, of course, additivity will be equivalent to have excessive coproducts. So this is formal and easy to state. Of course, you need a target of your homology to be a Grothendieck category if you want to have arbitrary direct sums, but that's not a serious problem. And so let me now introduce two other categories, which are Hom extra, which of C square A, and this is contained in Hom of C A. Okay, so this Hom extra is just the homology which satisfy all these excision and homotopy invariance axioms, plus the longest sequence, so the Eilenberg-Steenrod. This is the Eilenberg-Steenrod, but the point axiom. So if you add the point axioms as usual, so adding point. So we need to have a chosen point object or class or set of point objects. Adding point axiom, we have Hom, let's say, ord of C into A. Okay, so this is a ord decoration. So now you see that if you make A varying, you get functors. And the first theorem is the following. The first theorem, which in some sense is how to say, is summarizing the first plus two thing that I was mentioning before, is that the two functors now Hom C blank, then I said Hom point, which is again, then we have the relative Hom of C here, plus the Hom extra here, and the ordinary Hom of ordinary C here. And we also can add additivity. So let's say that we have with the capital Hom extra the additivity. We add additivity on this ord. So these, they take values in here. The variable should be Grothendieck category. Okay, because we want to have, assuming that C has arbitrary coproducts, additivity needs to take value in a Grothendieck category. All these functors, all these functors are representable. Of course, I mean two representable are strict two functors. Which means that in the first part, they take values in a small category. So you have, for example, let me take this one, home. For example, home C, the relative cohomology functor takes value from X to cat, where this is small abelian categories and exact functors. Okay, so, and this one is a Grothendieck category with the exact functors, but such that they preserve also filtered co-limits. So what does it mean? This means that this means that we have universal abelian categories and universal cohomologies in the following picture. So C goes to some abelian category AC. This is some H, which is a collection of functors, which is a universal. Then we have the functor here, which goes to the C square, and we have a relative. This is the universal relative homology in some category here. And in fact, there is a functor which goes here. This is exact, and the image of this functor is generating this one. So the image is given by the HI. So this category is generated by HI of X, such that in the sense that the HI generated a thick subcategory and the subquotient of them. And this is enough. This is generating everything in here, in this category here. And then we have a quotient, which is this point, if we add the point axiom. And here we have also a way to express the point axiom, and there is a quotient of C. And of course, there is an induced functor here. And then we can take quotients to A extra and C. And here we have A ord of delta of C. And there is, this is again a quotient. A quotient is an exact functor, which is a quotient in the usual sense. And then there are functors which goes to the bigger, where the additivity is also required, but are not quotients. Indeed, these are like in the completion. So this is ord of delta of C. And here I have, this is a small ord, this is capital ord. And if you have an excessive coproduct, this is ind of the other one. So it depends on the homological structure. They can be equal, or they can be zero sometimes, okay? If you take as an interval the zero object, you get the zero category. So it really depends on and this latter, this one, and this one are, as you see, Grothendieck categories. So these are still in the same universe, okay? So these are the size of this category is the same of the size of C. And when you you take in the completion or you quotient by taking in the completion and take the quotient by localizing subcategory, you get still in the same universe. So for example, if we take a top with the usual interval and the usual class of excisis square, you get what I define as topological motifs. Okay, in general, as far as I can say, the topological motifs are not easy to understand, are very big because the topological spaces are maybe too wide, is a kind of big category. And what I can say is something about the situation of CW complexes. So for CW complexes, I can really give a description of this category as you will see in the following. So I briefly say how to get this universal thing. So I would say universal representation theorem. Universal representation theorem is the following construction. If you have for any diagram the quiver, we have a universal representation. In an abelian R linear fixed ring, commutative ring with one, R linear, not Noetherian, any ring, linear category. That I call AER of D, and I show you how to get this very briefly. I have the diagram, then I can complete as a path category. Then I can make it an pre-additive enrichment R of D bar. This is pre-additive enrichment by taking free R modules on the maps. And then I can complete additive completion by taking string of object and matrices as maps. So this is additive completion. So now we get to this guy, which is an additive category. So this is an additive. This is additive R linear. And from this to this, we have the so-called Freyd's universal abelian category, which was introduced by Freyd many years ago. And by definition, this is an R of D. Okay, so this is Freyd's category. So you see all the steps, but this one. So the last step is as follows. And I revisited a little bit Freyd's theorem. So take R. So R linear additive category. Then you can make a two-fonter of internal R modules, which by definition are additive functors, are linear, from the R to the A. So A is abelian, okay? And the fact, the theorem, is essentially the Freyd's theorem. You can find also in books, is that this is representable. I mean, I rephrase it. You don't find in the book in the way I am representable. So this means that, in fact, how you get this? So, in fact, okay, so let me add R of this R additive category is equivalent to the following, is a category of R mod. What I mean by this, I mean that R mod, capital mod, is by definition a big category of additive functors from R to R modules. Okay, this is a big category, and then the small one, R mod, is by definition the compact object of this one. So this is finite presentation objects. And in this case are just co-kernel of representable functors. So what is the key example here? The key example of what is going on is the case of the additive category given by the completion of, this is a ring. Now I want a ring plus. So this is, so D is equal to single point. That means that D bar is 1. And in this case, we get that what I want to call R mod underline to be
There you go.
okay. So what okay, so yes, I was mentioning about this R mod, which by definition is add R. These are finitely generated modules into the big category of R modules. So additive functors from finitely generated R modules to the big category of R modules is this universal category of modules. This is the homology. I mean, in some sense, I mean, from the point of view of algebra is the universal category of modules. From the point of view of homology is the universal category, homological category of a point. So this is a point in the previous terminology of 1. So this is a bold 1. And yeah, this is R mod. And you see the difference. This is a big one, and this is the small one. So these are the compact object in this one. So what is the property of this category? this is representing the functor, because what is a homology on 1 point? So 1 point is the category given by the 1 point object, so which we declare to be the point object, and the identity of it. Okay. So as a diagram is just what it is, and what is the property here? An homology on this is just a functor, right? By the definition. So if A is equivalent to hom on point of 1 into A, to give an object is equivalent to give an homology on the point. And this is also equivalent to exact and are linear functors because of the representability theorem of hieratic finitely generated modules into A. So that means that if we have an object here, this yields a functor, which is a kind of a realization from R mod to A. And okay, because of the universality and the identity, okay, is providing an object which is the universal object. So R correspond to the universal homology, where R also correspond here to the identity of R mod to itself. Okay, and if this category is Grothendieck, then you can extend it to the big one. So you also have A to the big one, because this is the indization of this one. So you have 2A for this Grothendieck, and this is also preserving filter colimits. So what we have is that the hieratic R modules, this abelian, this Grothendieck category, is of course provided with a functor to R modules, the usual R module. But also, for example, to condensed R modules. And in fact, any Grothendieck category I can take the generator, and then I have a functor which is exact from R modules to this one. So now, if R is a coherent ring, such that the finitely generated R module is abelian, then this is a quotient, but it's not in general faithful. It's not at all faithful, and this is very important. Is an equivalence essentially if and only if R is what is called a von Neumann ring. For example, for a field, this is an equivalence. So the all difference between R modules and the usual R modules, the hieratic one and the usual R module, is given by torsion in some sense. Okay, so this is a very interesting category, and it's in fact the universal category for even for CW complexes. So I don't know how much time I have because I was interrupted. But so what is this? So we always have from simplicial sets to the chain. Of course, the same diagram we have for chain because are okay. So, and what is this functor? It's taking a simplicial set to say the sum over x dot of R. In some sense, is the free object on the R module, universal hieratic R module, and if R is a field, you see what I mean. If because this hieratic R module are usual R module. Otherwise, this is so this is giving a simplicial set, and then the simplicial set that you convert in a chain complex. So this is the chain complex given by the simplicial object. Okay. And so you can take, in some sense, a singular homology with coefficient in this universal hieratic R module, which is not the usual one, but is in fact the universal singular homology. So if you have a cosimplicial object of C, as usual, we can take the singular of X to be C of into X, and this gives a functor from C to simplicial sets. Now you compose with the previous one, and we have this implies that XY gives HI sing of XY with coefficients in the universal hieratic R module, and this is a homology from C taking cones R mod. Okay, and another theorem is that the subfunctor of homology, of a singular homology, of course, what I did here, I can do it for any Grothendieck category. So C blank of hom ord of blank. Okay, singular homology is also additive if we have coproducts and satisfy the point axiom if the cosimplicial object is such that I0 is 1 and I1 is the interval. So for some interval, okay, it's just an object, not and so this functor, this subfunctor, this one is representable. So this means that we have H sing from C to A sing, let's say, some category, which is in fact a quotient of because I cannot, if I have a homological structure, I cannot, I mean, there is no reason that a singular homology is an ordinary theory with respect to the homological structure. So if it is ordinary, then this A thing is just in of R modules. So otherwise, it is not. So this coincides with the hieratic R module in some good cases. In general, this is a Grothendieck category, and A ORD of C as clearly a functor from this to this one. And in this case, of course, it could be that there is no, it depends really on the homological structure, but it could be that this A thing is zero. I'm not saying that it's not zero, but usually in the good cases, like in topological cases, it's not zero. In fact, I also have that H thing in a singular homology in the ordinary category, and where these are not the universal R module, but the universal coefficients. So this is by definition H0 of 1, where I assume that 1 is a point object, a finite point object. Like in the topological case, or in the case of schemes, there is such a finite point object. And if, so note that if H thing coincide with universal ordinary homology, then this implies that the functor is an equivalence. Let's see, to this thing of C is an equivalence. Okay, and in general, there is no reason for, even in the topological categories, there is no reason for this to coincide. Like what we learned from Eilenberg-Steenrod is that as soon as the topological spaces are just CW complexes, then the ordinary theories are given by cellular homology. And now I can prove it very easily in some sense in this framework, which is a universal framework, and in fact gives a unicity of Eilenberg-Steenrod in a better simple way in some sense. So what is the next is a cellularity, and I give you a very quick idea of this. Suppose that we can filter by dimension. Suppose the existence of filtration by a dimension function. Which means that like for CW complexes, we have distinguish d-1 and so on x0, and then x-1, this is 0. So we have an initial object and some d dimension of x, and a filtration by these are sub distinguished monomorphism. Then any H, which is a relative homology with value in A, if the category has such a structure, and A is Grothendieck, then we have a spectral sequence, which is just the Niveau spectral sequence, is given by the limit over SP plus Q x P xp minus 1, where the limit is taken over all the filtration, and it converges to hp plus q in x. So I have a homological spectral sequence like this, and in fact, I can take m of x to be, by definition, the dot of E1 star star of x for H equal universal homology, relative homology. I don't need anything here. I just need that a relative homology theory. And this gives a factor m from C to the chain complexes of ind of A C, the universal category, ind of the universal category, which if we choose a homological structure on the category, we get to the order of C, the ordinary one. Okay, so we have this factor. Okay, this x is sent to this dot of E1 star star of x, and this here is if we have a cellularity. So what is a cellularity? So this is by definition. So we can always project, because there is a factor like this, but if we have cellularity, this total complex of this complex collapses to the cellular complex. If you have cellularity, by definition, the spectral sequence degenerate. By definition, E1 PQ degenerate. So with HP plus Q of XP, of SPQ of XP, XP minus 1 is 0 for Q different from 0. So you have only this, and then this means that we have a complex like this one, HP, which is the usual cellular complex, okay? So this is now complex, cellular complex, okay? And for example, as I was saying, this is the case of C equals CW complexes with the standard homological structure that I don't remember, but it is clear. So in this case, the singular, universal singular homology is cellular. So I mean here, this H cell is the homology of this complex, is the same of H single with the coefficients in the universal ring. And this is also H, the universal ordinary homology. Okay, so this is because every ordinary theory in this case is cellular. So for singular homology is ordinary in this case, and it is cellular. So it is isomorphic to the universal ordinary homology, because also the universal ordinary homology is cellular. Everything is cellular, and therefore there is no choice is seeing the universal category for CW complexes is equivalent to the ordinary one, CW, which is clearly hieratic R modules. And the universal ring, in some sense, the universal module is also the universal coefficients. So this also coincide. Okay, so for the situation in the topology, of course, we can apply this to finite topological spaces or sets, I mean, there are other situations where I think it is quite interesting to understand what is going on. So the very last thing that I have to say is about schemes. So in some sense is the conjectural picture. What about schemes with the ordinary, the standard, again, a standard homological structure? So in this case, we have schemes over a field, let's say, a finite type over a field, and so finite dimensional. We have the functor that I was saying before. This is going to chain complexes of ind of, so for it is going to the derived category, the big one, of ind of A of schemes over K. And as I said, this is going down from this one to the derived category of A or of schemes. But in this case, it is not true that this is not the correct one. So this is not enough to get a cellularity. So this projection here doesn't give that, let's say, a cellular complex. It's not enough. Okay, so you really need to put more axioms. So you need to go again, let's say, to a further quotient, which is something that I might provisionally call a dual, because we need some duality theory on schemes. Is a weak duality here. And okay, and okay, and then we know that we have already the functor from this to the Vygotsky here. Okay, and oops, my God. Okay, and now this what we want is that the functor decomposition that we have here is making M of X a homotopy invariant. So M of X satisfy homotopy invariant, and for a choice of good topology compatible with topology. So by universality, we should get a functor like this. Okay, but okay, for example, if K is in C, okay, we have that A ord of schemes over K goes over by definition in some sense. This is the definition of Nori. Motives is the factorization of the realization functor that I have from these two R modules, but usual R modules, not the hieratic ones. So you have a realization functor given by the singular homology, right? R is singular, usual singular homology into all R modules. So R is not Noetherian, it's everything. So we have a factorization like this. This has a quotient and a faithful functor here. And this gives this D to Nori here. And we know that at this level, using singular homology, there is a cellularity for this quotient, but this is a bigger quotient. I mean, this is maybe too big. So this quotient has very good properties, and there is like the fact that we have this one, and one expects this to be fully faithful, but this is a very big conjecture because it implies the standard conjecture. And so what I expect is that the conjecture here is that is a weaker conjecture, is that dm is in fact fully faithful inside the D of some A dual of schemes, so which is a weaker conjecture. So if this is now fully faithful, okay, then maybe we have even, I think that this factors through this, but okay, but this, because all the properties of this dual are inside the theory of singular homology. So singular homology has a duality property, which is only one axiom. So in some sense, from the free, this is the free category, homological category, you take quotients, okay? So this is essentially going down, taking quotients. And what you do in with Nori construction is that you take just a homological functor with all the properties you need, but you don't know how many properties you are using. And this theoretical path make in some sense clear what are the properties that you are using in order to get the minimum embedding in some triangulated category like this. And if this is this conjecture is now true, then you see if this is a triangulated functor, you get a T structure on Tn, which has as part this abelian category. So this implies in some sense that, of course, in weak sense, mixed motives are equivalent to are given by this A of dual. Of course, this doesn't imply at all faithfulness conjectures or conservativity conjecture. This is the conservativity is related to this functor. So from Vevosky to Nori, but not from this to this one. So this is essentially everything. So okay, I don't know if there is somebody there willing to ask questions.
Yeah, so first let's thank Luca. Yeah, thank you. Yeah, we'll see if there's some questions. Anybody?
Yeah, hi Luca, Paul Arne here. I got a question in the conjecture there at the very end. On the right hand side, it's you're writing schemes over the field. Did you use a topology on schemes to this category?
Okay. Yes. No. This is in some sense here at this level. DM is with the Nisnevich topology, and this conjecture the last to be safe is in the situation of a Q linear. So you are right. Most probably is with the DM et al. Everything is going smoothly with the standard homological structure on schemes, which is given by the usual pair of, given by closed immersions, and the excisions square are those which you have two closed and you take the intersection and the union, right? Okay, so this is essentially the topology. This excision, choice of excision gives a topology every time, because there is a CD structure on your category. So this generates a topology, a CD topology. So in some sense, there is, if you want, this CD topology of Vygotsky. And the other one, the other property of homotopy invariance is related with the choice of an interval. Okay, so the topology is in excision, if you want, and the interval is, of course, related with the homotopy. So you see the two ingredients here, DM, and you have a choice of a topology plus the homotopy invariance.
Thanks a lot. That's very clear. Thank you. Thanks.
Okay.
Any other questions? Okay, last chance questions. Come on. All right. Well, thanks, Luca. We'll stop here.
Thank you. Thank you.